Hello, everyone. Welcome to our lecture. This is our second lecture dealing with Chapter 2 in the text. And we're talking about atoms and the periodic table and solids, liquids, and gases. The concept of the atom has been around for a very long time. Even from the ancient Greek Democritus theorized that all matter was made of small, indivisible particles called atoms. And even in John Dalton's time, we have Dalton's atomic theory that, at this time, people had no means to even investigate their claims. And even with John Dalton's time, we didn't even really have the means to know what was inside an atom, but we still have the same basic ideas. Elements are composed of small particles called atoms. Compounds are more than one atom that's joined together. And chemical reactions are simply when atoms rearrange each other. This is a really important fact. A lot of people think chemical reactions involve destroying atoms and creating new ones, and that's not the case. Even the chemical reaction in which we burn the natural gas on our stoves, the methane, the prime ingredient in natural gas, is carbon connected to 4 hydrogens, and it reacts with oxygen in the air. And those atoms simply break their bonds and rearrange to form bonds forming carbon and oxygen, forming carbon dioxide, and even water, hydrogen and oxygen combined. So chemical reactions do not destroy atoms. They rearrange atoms to form new chemical compounds. Over time, and by no means do I expect people to memorize individual concepts of the discovery of the electron, but we were able to understand the atom piece by piece, and one of the first discoveries was of the electron. We knew that if you made a device called a cathode ray tube, you took a glass and hollowed it out and put a vacuum on it. And we knew if you put a large positive charge across this, we have a positive plate and negative plate and positive plate, we can actually pull electrons off of material. We didn't know what they were, but we knew that these electrons could travel through this glass tube and hit a phosphorescent screen down on this end. When we started to get really creative about this, we said, well, you can take and put a magnetic field here, or magnetic field going across, or an electric field, and these particles will actually deflect. So if you notice down here, we have this positive plate right here. If you notice these, whatever these charged particles are, they actually deflected towards the positive side. So we know these particles have to be negatively charged, opposites always attract. So we end up understanding the concept of the electron. Similarly, this was a famous experiment done by Rutherford. Rutherford took a radioactive substance, and there's a big misconception that radioactive substances are always dangerous, or that they'll turn you into the Incredible Hulk. Obviously not true. But if you take a radioactive substance like uranium, radioactive substance simply means this substance is not stable on its own and will usually decay into smaller atoms. So you take a radioactive substance and you place it deep inside a lead block. Lead is very good for blocking radiation. As you know, if you've gone to the dentist, they put a lead apron on you before your x-ray. If you take this radioactive substance, it will actually emit certain rays. And we really didn't understand what these things were, but we knew if you pass these rays through an electric field, we get 3 interesting things happening. One part of these rays actually get bent downwards, and again, if something is being bent downwards, it has to be attracted to this. So these alpha rays, we know now as alpha particles, they are actually very similar to helium atoms. Beta rays are attracted to the positive plate. They are our electrons, and these things called gamma rays are actually the highest energy form of light that we know of. So understanding the basic particles helps us further understand the atom. Eventually we understand and discover the neutron later on, and we discover that. So you can read up on the discovery of the atom in great detail, but we understand that the atom is made of protons, neutrons, and electrons. The protons and neutrons occupy a space we call the nucleus, very similar to cells. And the nucleus occupies the space in the center of an atom, and it is extremely small. Electrons tend to take up the periphery, and what we understand now is most of the atom is empty space. We have protons and neutrons in a tiny spot in the middle. Electrons are on the periphery, and inside is empty space. And people are tempted to say, well, that means the inside of an atom is filled with air. Well, that would be impossible because air is made of atoms. So the inside of an atom is truly a mystery, but what we're going to take a look at next is kind of really taking apart and how do we know how many protons, neutrons, and electrons an atom has. And it's very predictable once you understand the relationships from the periodic table. Protons, electrons, and neutrons are very, very small, and they have incredibly small masses. You notice the electron is almost 4 orders of magnitude. 4 orders of magnitude is approximately 10,000 times lighter than either the proton or neutron. Proton and neutrons are very similar in mass and are often thought of as being the same mass. The difference comes in with the concept of charge. Neutrons are neutral, they have no charge, whereas protons are given the charge of +1 and electrons are given the charge of -1. The actual value of the charge is not necessarily important right now, but you can use this later on in chemistry too. If you actually look at the periodic table, and you'll all get your very own copy of the periodic table Thursday night, the periodic table can be very short. Other periodic tables you have can have lots of information, but the essentials about protons, neutrons, and electrons, as well as the name of the atom, are listed on here. The elements are usually given a simple symbol, usually the first letter of the element's name. Some elements have a second letter, which is usually in lowercase, and in this case, this is the element carbon. Some elements we've known for quite some time. So, for example, the element sodium is not printed as SO, but rather after its ancient name for natrium. So don't let this worry you that certain elements have different names than you'd expect. It just kind of is what it is. I apologize for my spelling here. There we go. I corrected myself. So after you see the symbol, there's 2 really important pieces of information on the periodic table. And the first is a small number on top. And this small number is what's known as the atomic number. And all atomic number really stands for is the number of protons an atom has. Now we know that neutral atoms also have to have exactly the same number of electrons. So if you look at this number, you automatically know the number of protons and electrons an atom has. So it's always very easy to determine the number of protons and number of protons and electrons for any atom. The number on the bottom is actually the average mass of the atom. For all intents and purposes right now, the best thing you could do to kind of simplify matters is just round this to a whole number. And we'll talk about this in a moment, why this is actually a decimal number instead of a whole number. So the average atomic mass we can get just by adding up the number of protons and neutrons for any atom. So if you have an atom like carbon, and carbon has a mass of 12, we can work backwards. If we know that 6 of these are actually protons, so what's left over has to be neutrons. And again, the decimal number is simply because some atoms happen to have more or less neutrons than others. Again, we'll talk about that in a minute. So a simple way to always find the number of neutrons in any atom is just to take the mass and subtract the number of protons from it. So for example, to find the number of protons in titanium, we just say, oh, that's equal to the number on top, the atomic number. So titanium will have 22 protons. We also know it has to have the same number of electrons. And the mass, we can take the mass and subtract the number of protons to get the neutrons. So we end up with a number 47.9, and right now we could just round that to 48. So 48 minus 22 is going to give you 26 neutrons for titanium. So this is the way we do this. Just with a simple amount of information on the periodic table card, we can find all 3 of these things. And there's actually a lot of wealth in that this is simple, because the two most important things, or two of the most important things we need to know for when we talk about chemical bonding, is the number of protons and electrons. One thing we have not commented on right now is that the number of protons and electrons have to be the same because they have opposite charges, and atoms do have to cancel out their charges in order to remain neutral. So I mentioned a moment ago that some atoms can have more neutrons, and these are things that we call isotopes. And it's very hard to determine directly from the periodic table the number of isotopes that each atom has, but for a very quick example, the atom hydrogen actually has 3 isotopes. Hydrogen, what we call deuterium or tritium. And the difference here is, if you think about the example with just hydrogen, hydrogen has a mass of 1 and has 1 proton, so it can have no neutrons. So if you're working this out, this version of hydrogen has 1 proton and 0 neutrons to get a mass of 1. Deuterium always has to have 1 proton. And if I didn't mention this before, it is the number of protons that defines the atom. For deuterium to have a mass of 2, it would have to have 1 additional neutron. Tritium is also hydrogen, but with an additional 2 neutrons. So it has to have 1 proton. Whoops, forgot the line there. 1 proton, 2 neutrons to give you a mass of 3. Now, the thing to do is take a look at the periodic table and take a look at the average atomic mass for hydrogen. Okay, average atomic mass for hydrogen is 1.008. So think about this as an example. Imagine you had a class full of hydrogen atoms. And if all hydrogen atoms have a mass of 1, let's just say, for example, if I have 100 hydrogen atoms in my class and they all have a mass of 1, if they all have a mass of 1, the average for the mass in that class should be equal to 1. All right, hopefully that makes sense. If everyone has the same mass, we add all the masses for the people, divide by the total number of people, we get 1. But what if 1 or a few of those people has a mass of 2? What would that do to the average? Let's imagine just really quickly, 1 person has a mass of 2. Well, if you go back to average all those people again, the average can no longer be 1. It has to be a tiny bit bigger than 1. So that's really what we're seeing here for hydrogen. And after seeing the example of deuterium and tritium, this 0.008 tells you that hydrogen has to have isotopes with more than 0 neutrons. Okay, so if you look at any atom and you see a decimal, you kind of get the sense that, okay, I know how many neutrons this atom has to have. In the same token, you can almost tell by looking at the average mass what are the 2 most common isotopes. And perhaps hydrogen is a bad example. Let's do another example in a moment. So let me take the atom phosphorus. So I'm looking at the atom phosphorus right now, and I know that, well, phosphorus has got to have, if the mass is 30 and it has 15 protons, it has to have at least 15 neutrons. But if I do the math on that, 15 protons plus 15 neutrons gets me a mass of 30, and the average mass is 30.974. So the only way I can get an average bigger than 30 is if some phosphorus atoms, some of them, and maybe we can comment on that, on how many, have to have a mass of at least 16. Now, it's no way to know right now, just by looking at this number, that the isotopes have to have a mass of 16. It's possible that they have more than 1 additional neutrons. But that's what we can get from here. So by looking at the average, and by looking at the masses on either side, we could say a mass of 30 and then a mass of 31. If we look at the average between these two, the average is a lot closer to 31, right? 30.974 has to be a lot closer to 31. So we can kind of say that it's more likely to have an isotope of phosphorus that has 16 neutrons than has a mass of 15. If it were the other way, if the 15 neutron isotope were more common, we would expect this average to be closer to something like 30.1 or 30.2. Okay, you follow me on that? All right, so there's something else I want to show you. We can actually represent atoms in what we call isotopic notation. Okay, so isotopic notation can be written two ways, and it's really to represent the number of protons and neutrons in an isotope. And we write it like this. The element X just stands for the element symbol, and for the heck of it, I'm going to choose the element carbon for this. And the number on the bottom is just the standard atomic number, so the atomic number for carbon is 6. But the number on top is a little bit different. The number on top is technically what we call the mass number, and chemistry and physics are noted for terminology that doesn't necessarily mean a whole lot, and mass number is no exception. But mass number is literally the number of protons and neutrons. So I know that carbon, or some carbon, should have a mass number of 12. And 12 stands for 6 protons plus 6 neutrons. Following me? Well, if you might recall, the average mass for carbon is not equal to 12. It's actually 12.011. So what that means is that some carbon atoms have to have a mass, have to have more neutrons, possibly one more, possibly two more. So this other type of carbon, this other isotope of carbon, would still have to have 6 protons, but this isotope would have to have a mass number of 13. So this is what we call isotopic notation. And if you notice down here for the hydrogen, again, if the number on the bottom is the atomic number 1, the number on the top is the mass number. This basically says there's no neutrons for this atom. This isotope deuterium has to have at least one neutron plus one proton to get to a mass of 2. Okay, so this is a very standard method of isotopic notation. There is another, and the way we would represent the isotope of an atom is simply to take the element, like this case, isotope for carbon with 12, a mass of 12, and literally write the name, carbon dash 12. So this isotope with a mass of 12, or a mass number of 12, would just be carbon 12. And this might be more familiar to you. You might have seen something like this before. Carbon, this mass would be carbon 13. And so, and if you are familiar with radiocarbon dating, you may be more familiar with the carbon 14. And that is a form of carbon that is radioactive and decays over a very specific amount of time, and they use this on bones to determine the age of the bone. Basically, so it's a very useful concept. But this is what we mean by isotopic notation. Okay, and here we are with the granddaddy of all patterns, what we like to call the periodic table. The periodic table represents every element that we know that exists today. And currently there's 118 elements. There are 26 elements that are formed normally in the core of stars. Not our star. Our star only forms helium. That's its prime job. Element up to element number 92. Element number 92 is uranium. This is the largest element found naturally, and we understand that from our understanding of science that stars are the prime places where elements are actually formed. Elements inside of stars are formed in a process called nuclear fusion, and for example, our star takes hydrogen atoms and actually squeezes them together under extreme temperatures and pressures, and the nuclei actually merge to form a new nucleus, and in this case we make the element helium, and larger stars make larger and larger elements all the way up to element number 26 for iron. And I mentioned before that uranium was the largest naturally occurring, so if the largest element made in stars is iron, then we have to have a method for forming other elements, and it turns out this is all the elements after iron are formed during a supernova explosion. That's our current understanding of element formation. But there are a lot of patterns in the periodic table. There are maybe some things you're not quite sure of, what the different colors mean, and so on. Why some of them seem to be numbered very correctly, 37, 38, 39, 40, but yet when we get down here, we seem to skip from 56 to 71, and we have these other elements which are grouped out of the way. And these are all questions that we'll answer with time. But the periodic table is composed of mostly metals. And if you're looking on the screen, all of the elements up here that are in gray are actually our metals. So it may surprise you that this entire area of the periodic table, most of the atoms you come across on a daily basis are actually metals. Not all of them. You don't come across all of the elements on a daily basis, but a fair number. There are atoms over here listed in blue, and this is usually this upper right-hand corner. These elements are not metals. There's also hydrogen over here. So if they are not metals, they don't have the property of metals, they have to be things we call nonmetals. So metals and nonmetals behave very differently. If you think of your stereotypical metal, it's a great example of all the properties of metals. Metals tend to be very bendable. The technical term for that is malleable. Metals are ductile, which means you can take them, pinch them, and draw them into a wire. Metals are very shiny. They have the technical term luster. They are also excellent electrical conductors and thermal conductors, which is why we use metals like copper for our electrical wiring, and we use silver for some types of electronics because of its very high electrical conductivity, and gold just because, well, it looks good. But metal elements all have a purpose. The periodic table is oriented two ways. Top down are things we call groups, and left to right are things we call periods. And I don't mean to imply that this is just a period here. All the periods, and there are 7 of them down across the periodic table, are horizontal, and groups are top down. We have 18 groups and 7 periods. If you notice, there is an interesting numbering system on here. You will find the numbers 1 to 18, but for purposes of looking at patterns, we look at the prime 8 groups, the groups that usually have, there's usually a Roman numeral here, 1A, 2A, 3A, 4A, 5, 6, 7, and 8A. Those are the groups we'll be spending most of the time with. The groups in between, if I can get this on there, the groups in between, the groups between 3 and 12 are a special type of metals we call transition metals. These are metals that can have multiple colors depending on the condition. Many of the metals that we use for interesting things like titanium and iron and cobalt are found in this category. The last category of materials in the periodic table are the elements grouped in orange. And if metals are shiny and bend easily, and nonmetals are dull and are brittle and are poor electrical conductors, metalloids are things that are kind of in between. The most important metalloid in existence probably is the element silicon. Silicon can be changed a little bit by adding usually a little bit of phosphorus or a little bit of boron to conduct electricity in a very controlled manner, and is the basis of many computer chips today. So metalloids have properties in between metals and nonmetals. Some periodic tables also list whether the element is a solid, a liquid, or gas at room temperature. And I can tell you that almost all metals are solid at room temperature. There is the metal here, gallium, that will melt with the heat of your hand. And the metal mercury is one of the lone stragglers that is a liquid at room temperature. All of the metalloids are solid at room temperature, and many of the nonmetals are gases at room temperature. There are very few nonmetals that are solids. Carbon, phosphorus, sulfur, and I believe selenium and iodine are several of the nonmetals that are actually solid at room temperature, but the rest are gases. Bromine is a notable exception. Bromine forms a liquid, and this is not normally information we expect people to remember, but it is very important to remember that most nonmetals, oxygen, fluorine, chlorine, and as well as all of the noble gases in group 18 are gases. Some of the groups in the periodic table have names, and we have also already mentioned the name of the 10 groups across the middle called the transition metals. The first group of atoms is extremely reactive. These are called alkali metals. The second group are alkaline earth metals. The last group all the way to the right, noble gases, followed by the halogens, followed by the chalcogens. And the names of the groups are fairly important as time goes on, but one way we learn about the different numbers of isotopes an atom has is by performing a measurement called mass spectroscopy. And mass spectroscopy, or simply mass spec as it is abbreviated, is a pretty simple technique, and a lot of this equipment can be miniaturized. So if you're looking at something like looking at a crime scene, and you're trying to detect very trace amounts of materials that may be present, a mass spec is really the way to go. And you simply take your sample, and you do have to atomize it. You have to somehow turn it into a gas and pass it through a very strong electrical field, which causes the atoms to fly through this chamber, which is also evacuated. And then what they do is pass the atoms past a magnet, and that causes the different atoms, or in this case ions, to deflect, very similar to how light will deflect through a glass prism. And based on the degree of deflection plus the amount of contact points on the detecting screen, we can detect the masses of atoms. Obviously, the heaviest atoms are deflected differently than the lightest atoms. So in this case, we can look and see the relative abundance of this particular atom. This is neon. That means this atom with 10 neutrons is much more likely to be found than the isotope with 11 or even 12 neutrons. Atoms can become ions, and one of the things we didn't mention before in the periodic table is that all atoms are neutral in their ground state, and that means that all atoms have the same number of protons and electrons. And we're just demonstrating the sodium atom here. So we know that sodium atoms have to have 11 protons and 11 electrons, and the reason for this is because protons all have a charge of +1. So that's a strange concept. It's a strange concept to think of an atom as having a +1 charge instead of just positive charge or negative charge, but you can really think of it as a quantity of charge. So 11 protons that all have a charge of +1 will give us a +11 charge. So likewise, electrons having a -1 charge, 11 of them will add up to a -11 charge. So we know an atom is neutral when we go to find the sum of all the positives and all the negatives, and we get 0. So for our standpoints, 0 means neutral. Well, for purposes of stability, atoms will want to either get rid of electrons or gain electrons. So as I said, there's only a few atoms in the periodic table right now that are neutral and stable. And I'm not referring to stability in terms of a radioactive sense. I'm just saying these atoms would, if you personify it a bit, these atoms would like to react to become stable. So one instance is sodium is an atom that would prefer to get rid of an electron. So when it does that, the core of the atom remains exactly the same. An atom like sodium keeps its 11 protons, so it still has a +11 charge in its nucleus. But if it's lost or deficient one electron, now it only has 10 negative charges, so its negative charge is -10, and as you can see, that leaves a deficit of one electron. If you do the math, you don't end up, when you lose something, we don't end up negative in this case, we end up as a positive charge. So if an atom loses an electron, it actually becomes positive overall, and that's just because of the charge balance. So when an atom loses an electron, it becomes an ion. Specifically, when an atom loses an electron, it becomes what we call a cation, or simply an ion with a net positive charge. Again, sodium does this because it wants to become stable, and we will talk in great detail why an atom would want to become stable by getting rid of an electron. Similarly, nonmetals tend to want to gain electrons to become stable. So the atom chlorine has 17 protons, 17 electrons. That gives us a plus 17 charge and a negative 17 charge, which cancel out to give us 0. It is neutral. But if the chlorine atom gains an electron, and it is common for nonmetals to gain electrons, the charge balance is again upset. 17 positive charges, and now an additional electron brings its charge with it. We now have 18 -1 electrons, or a charge of -18. So again, this is a strange concept. If you go to add these together, I just said that a little wrong, but you'll figure it out. If I go to add these together, I don't get a positive one. We normally think of gaining something as you have more, it's plus, but not in the case of electrons. If you gain an electron, you also gain its charge. So we end up with a total charge of -1. So we've also created an ion, a negative ion, but this time we end up calling this an anion. And it's important that you do understand the difference between cations and anions, or cations and anions, as they're also called, but it's okay just to refer to them as ions. So sodium chloride is what we like to call table salt. The sodium in sodium chloride is, people often refer to it just as a sodium, but it's actually the compound sodium and chloride. Compounds often have completely different properties than their parent elements. If you think about the element sodium on its own, it is incredibly reactive, will react in the palm of your hand, will steal electrons from water and form hydrogen gas. Chlorine is a deadly poison. Bring them together in a compound, and they're delicious. We put them on our French fries. So a compound like sodium chloride is actually an ionic compound because it consists of ions, this cation sodium and the anion chlorine. So compounds have very different properties from their initial atoms. A covalent compound like water is a great example. The hydrogen in water is explosive. The oxygen in water is flammable. Put them together, and you can go swimming in it, and it's safe. There are some patterns in terms of the periodic table, in terms of when atoms form ions and how many electrons they gain or lose. And one of our first activities is to focus on the main 8 groups. Those are the groups with the letter A after them. And if you notice, all of the atoms in group 1 tend to lose 1 electron to become a positive 1 charge. Notice that there are some cases where books, instead of writing the element cesium with a positive 1 charge, you will just see it written as a positive. And in some cases, like for the element or the ion barium, I prefer to write this as barium plus 2, which means barium has lost 2 electrons, but you will also see it as barium 2 plus. Try not to get confused. So again, everything in group 1 tends to lose 1 electron to form a plus 1 charge. Everything in group 2 tends to lose 2 electrons to become a plus 2 charge. If you skip over to group 3, these tend to lose 3 to become plus 3 charges. Group 4 can kind of go either way. If you go down this group, you have metals on the bottom and metalloids and nonmetals. So the rules or predictability is a little bit out. We end up with group 5. These are atoms that typically want to gain 3 electrons, therefore -3. Group 6 wants to gain 2 to become -2. Group 7 gains 1, become -1. And group 8, they have no charge because these are atoms that tend not to want to react. In the middle, we see something a little bit different. These are the transition metals, and they're often very hard to predict. They are called transition metals because they can have different charges. The element chromium, for example, can either give away 2 electrons or give away 3. And this does depend on the circumstance. It is the different colors, it is the different charges of an atom that can determine its color. These are often very hard to predict, so we usually rely on a chart or something to help us out. There are naming systems for certain ions. For transition metal ions, when it comes to actually naming the ion or naming the compound that that ion is in, we have a slightly different naming system. If we know that the charge of the ion, and by the way, another name for charge is what's called oxidation state. But if we know the manganese is a +2, what we're going to write when we name it is manganese with a Roman numeral 2. If you notice, if we were to name all these 3, they're all manganese, but they make very different compounds. So it's appropriate when you have a transition metal to actually use a Roman numeral when you're naming this. Let me just give you a quick example. So for example, these are 2 chemical formulas that involve the iron ion and oxygen ion. The problem is, unless we knew exactly what charge they were, we would call both of these compounds iron oxide. And that's a problem because they have very different chemical formulas. Materials with different chemical formulas behave differently. So when we go to name these chemicals, it's important to also include the Roman numeral that specifies the ion. In a few minutes, we'll talk about how to determine the ion charge of both of these atoms. But I know from experience that oxygen typically forms a -2 charge, and iron, because it has to balance out the oxygen, has to form a +2 charge. So if I named this specific form of iron oxide, it would actually be iron Roman numeral 2 oxide. This form of iron oxide that we have here is actually iron that is in the +3 state. So this would be named iron Roman numeral 3 oxide. We just do this because we have to keep track of chemicals. Chemicals that have the same atoms in them are not going to behave the same. There is an older nomenclature system for atoms with different charges, like transition metals. And this is something that I typically don't make people memorize. Just using the stock system with the Roman numerals is sufficient. So, for example, the Fe+2 ion is ferrous, and Fe+3 is ferric. So in the example I had before, Fe+2, I could, instead of calling this iron 2 oxide, I could solve this just ferrous oxide, and this one would be ferric oxide. You're going to see that once in a while, but I typically don't teach that. I just use the stock system with Roman numerals. Okay, when we do name compounds, and typically we are talking about just ionic compounds right now, we usually just say the name of the first ion that's there. And by convention, ionic compounds are typically metal ions chemically bonded to nonmetal ions. And it's just standard to write the metal ion first. There's no really good reason for it, except that's the way it's always been done. So if I wanted to write the compound sodium chloride, I would write the metal ion first, followed by the nonmetal. So if you notice in this particular slide, when we do name a compound like this, we just say the name of the first element. So this is just sodium, and we change the wording of the last element. We remove a few letters and add the letters IDE. So that's a fairly straightforward naming system. So the chloride is just the ion form of chlorine. So when you do see this, if you saw the formula or the expression sodium chloride, you would just know that this represents the chlorine ion. And we know that because certain elements always form the same charge, for example, chlorine always forms a -1 charge, we would just know by looking at that actually represents the chlorine -1 ion. There are some ions which form from multiple atoms or groups of atoms. And we end up calling these things polyatomic ions. Poly for the prefix many, atomic for atom, so they are many atom ions. And these are things that just happen. They may look complicated, but they just kind of happen in nature. For example, the carbonate polyatomic ion forms when the carbonate ion forms when 3 oxygen atoms combine and chemically bond with carbon. It's a point of order, by the way, that typically when you see non-metals bonded to each other, it's usually not an ionic compound, it's usually covalent, but even though these are actually covalent bonds, and we are getting a little bit ahead of ourselves, the entire grouping of material ends up being a -2 charge only because inside here are 2 additional electrons. So it's a little strange. We have covalent bonds, but yet it ends up acting as a group, an ion. So these types of things are very common, and usually you end up remembering a few, and then we just use a table to kind of help us. So I'll pass out a reference sheet in class. I mentioned this a few moments ago that ionic compounds are really straightforward compounds in that they form because you have atoms that are unstable that want to become stable. So an atom like sodium tends to give an electron to an atom of chlorine to form ions, and these atoms will combine together to form something we call a crystal. By the way, from last week's lecture, this is something that could end up forming what we call a network structure of interlocking sodium and chlorine atoms repeating over and over again millions or trillions of times in all 3 directions. Because this is an ionic bond, these atoms are all just attracted to each other. If you think about it, I have a positive ion attracting and sticking, non-technical term sticking, to a negative charge. So sodium chloride is nothing more than individual ions that are attracted to each other by coulombic forces. Unfortunately, it would be a poor idea to build a bridge out of sodium chloride because these ions do dissolve in water. So even though this forms a network structure, a structure that forms many, many connections, according to my definitions last week, you're not going to build a house out of it. Okay, so now I want to talk about 2 things. I want to talk about writing chemical formulas. Once we know that certain atoms tend to form certain ions, we can start to make chemical formulas as a result of this. Right now, we're going to make ionic chemical formulas. So you can really start writing ionic formulas before you even understand the process of ionic bonding or even understanding why these atoms or ions tend to want to connect to each other. So one of the most important things you need to know in order to create your own ionic compound is that the end result has to be neutral. So what we're really looking at here are the excesses of charges. So again, if I want to make a simple compound like sodium chloride, I know that sodium is, if it does form an ion, is an ion that is missing an electron. So it has the net charge of +1. Now we know from our discussion before that the sodium ion still has 11 +1 protons. Right now it just has only 10 -1 electrons. So if I want to form a compound with an ionic compound, I need a metal ion and I need a non-metal ion. So I can use the element chlorine. And chlorine is a -1 ion. It's the net charge of it. I know that chlorine has to have 17 +1 protons. So in the nucleus is a +17 charge, but because it has a -1, chlorine has gained an additional -1 charge for a total of 18 -1 electrons. So if I want to make an ionic compound, I have to realize that the net charges have to balance or cancel each other out. So if I were to take a look at this compound and say, hey, can I make a compound from this? Do I need any more sodiums or any more chlorines? Maybe I need different whole numbers. Maybe I need 2 chlorines or 3 chlorines for a specific compound. The net charges have to add to 0. So if I just look, I know the net charge for sodium is +1, and the net charge for chlorine is -1. If I then try to find the sum of these, a +1 and a -1 cancel to 0. So we know that in order to make an ionic compound from sodium and chlorine, I only need 1 of each. So I can then just write the chemical formula as NaCl. This gets a little bit more complex when I have atoms with different charges. For example, if I had calcium and chlorine. So in this case, the calcium is an atom that's actually lost 2 electrons, and chlorine has only lost 1. Well, we know in the process of ionic bonding that calcium gives an electron to 2 chlorines. But if you think about this differently, one of the ways we want to kind of think about this is if we use the same method above and I write down, hey, calcium is a +2 charge and chlorine is a -1, well, a +2 and a -1 do not get to 0. They get to a +1. So what we're saying is here, I can't just combine a calcium and a chlorine and expect to get a compound. I need something else. In fact, in order to make this expression work mathematically, what do I need more of? Do I need more +2s or do I need more -1s? I think you can see that you need more -1 charges. So how can I get another -1 charge here? Well, the best way to do it is to get another chlorine. So in this compound, if I added in another chlorine, had 2 chlorines, 2 chlorine ions specifically, and each chlorine ion had a -1, 2 plus a -1 plus a -1 does add up to 0. So what this tells me is my compound has 1 chlorine ion and 1 calcium ion and 2 chlorine ions. Now, the way we represent this is, again, we put metal ions first, and then we have our nonmetal, and you may imagine, you may want to write the compound like this, CaClCl. It makes sense, but chemists love to simplify things, and the way we simplify a compound like this is by using a subscript to represent the 2 chlorines. So instead of writing the compound like this, we're going to simplify and use a subscript 2, and the subscript always goes after the element that is representing. So this compound becomes CaCl2. Vice versa, if I was giving you this compound, calcium chloride, and I wanted you to identify the ions that are present, there is another method we can use to talk about that, and we'll talk about that in a moment. So let's do a more complex problem. So the problem I want to use now, I want to take a metal ion, sodium, and combine it with a polyatomic ion. So the thing to remember, a polyatomic ion, the way I've written it right now is to say that the entire ion, the phosphorus and the 4 oxygens combined together, all add up to a -3 charge. So if you wanted to, I suppose you could insert just the variable x in here, and x would be this element with a -3 charge. But again, I want to make a compound from this, and I need to see how many of each of these species do I need. And if I wrote down my +1 and I write down my -3 here, and I sum them together, it's clear that I do not get 0. So again, you have to ask yourself, well, what do I need? Do I need more negatives or do I need more positives? And I think you can see you need more sodiums. In fact, you need 2 more of them. In order to make this compound work, you would have to have 3, whoops, I wrote the word 3. You'd have to have 3 sodium +1s. So 3 sodium +1s will cancel +1 here and a +1 there. +1 +1 +1 -3 does get to 0. So the way you write this compound is a little bit different. I put parentheses here right now, because I'm just trying to say this whole thing is represented by a -3 charge. You don't necessarily need parentheses in the answer. So I have 3 sodiums, and I represent the quantity by a subscript, not a coefficient. I do not write 3 out in front. So it's Na with subscript 3, and then the phosphate ion. I can just write here. I don't need parentheses around here. A lot of people are tempted to do it. Let's do another example where I do require parentheses. Okay, so here's my next example. I want to combine a calcium plus 2 ion as well as a hydroxide ion. So again, the parentheses are simply representing that the entire ion is a -1 charge. If I do my procedure here, I have a +2 and I have a -1, and we understand that that does not sum to 0. So we understand that in order to make this work, I need to have a second -1 charge, which means I need a second hydroxide. Okay, so in this particular problem, I need 1 calcium ion and 2 hydroxides. So now I have to represent this. And I could simply say calcium OH, and then another OH, but we understand we can simplify this. The thing we're simplifying here is the OH, and it is a group together. A lot of people might be tempted to write this as O2, H2, and that is incorrect because the hydroxide is the main feature, the main polyatomic ion. Writing the chemical formula this way, even though it is the same mathematically, represents a completely different compound. This would be CaO2H2, which would not have the same properties as calcium hydroxide. So I need to keep the OH feature separate. And because I have 2 of them, the way I would write this best is to keep the main feature in parentheses, OH, and then just use a subscript 2 to represent this. Okay? So this is the way we end up writing ionic compounds. There is a simpler way, and I showed this on the slide before. It is here. If I happen to know the charges of each atom, and by the way, this is usually given a name, the crisscross process. If I know the charges and want to write the chemical formula, all I have to do is literally cross, take the number value of the charge, and that becomes the subscript of the metal, and the number value charge of the metal, that becomes the subscript of the nonmetal. And this works every time you try it, almost every time, unless you're talking about something that, for example, something like Na, sorry, bad example. An example like Ca plus 2, O minus 2 does not go to become Ca2O2 because we can simplify. The simplest form of this is just Ca1O1. And again, if the subscript ends up being 1, we don't need to write it, so we would get rid of that as a subscript. So this works even if you have a polyatomic ion. The 3 from the phosphate ends up becoming the subscript for calcium. The 2 for the calcium ends up becoming the subscript for the phosphate. And it is important here that you have the parentheses here. If you did not have the parentheses for this compound, this would look like Ca3PO4 and then 2. So the outside observer would see calcium 3 phosphorus O42, which is obviously incorrect. So this is why we need to put the parentheses around the phosphate to represent it as its own group. Okay? Okay, now I want to go on to naming ionic compounds. Let me just say this. In general, most ionic compounds do not need Roman numerals. But if you are dealing with an ionic compound that has a transition metal in it, it must 99% of the time have a Roman numeral in it. And that's really unfair, and I'll talk about some of the exceptions, but especially if you're using the online homework. Naming ionic compounds, sometimes you actually have to go back through, in order to name it, you actually have to know what the charge of the atom is. And for example, in this case, if I want to go to name this, we remember we just literally say the name of the first element, and this element is sodium. But then I have to know what this thing is on the end, and this thing on the end is not carbon oxide. as you gain more practice, you'll realize that CO3 is actually the carbonate polyatomic ion. So to name this, I'd have to write this as sodium carbonate. So how come I'm not taking the name of carbonate and chopping off the last few letters and adding IDE to form carbonide? Well, because it already has a name. CO3 represents the carbonate ion. So this is the correct name for carbonate, for sodium carbonate. The point I want to make now is if I wrote the word sodium carbonate on a piece of paper, it only represents one compound in the entire universe. It represents this. It is completely unambiguous. Okay, this compound over here. You are looking at the iron and you're looking at the oxygen. You say, oh, this is iron oxide. So you go and you write down iron oxide. Well, we have a problem. And the first is that iron is a transition metal, which means it can have multiple charges or oxidation states. So the problem is this: if I wrote down the word iron oxide on a piece of paper, it could actually represent several different compounds. And if we are talking about chemistry, it's very important to have the right name to the right compound. Otherwise, you can have adverse chemical reactions take place. So in a problem like this, it's a little bit more complex because you actually have to work backwards to find out what the Roman numeral to put in here is. So we always have to start with something you know. And because the iron is a transition metal, that's the thing we're the least sure of. However, the oxygen, we are very sure of. If you go back to your periodic table, and you might even want to make a little reference to this in terms of what atoms have what charges. And again, I would only do this in the main group, the elements that have the A after their name. Well, oxygen is in group 6, which means it takes 2 electrons. So it always becomes a -2 charge. So that's something I'm very sure of. So take that information and go back to the problem. So if oxygen has a -2 charge, I know that this is a neutral compound. It is correct. If I go to perform the analysis I made before, where I was adding charges together, I take some positive charge, which I don't know what it is, and I add it to a -2. Now this looks a little bit bulky because plus a minus is really a minus. This whole thing should equal 0. So if this is the case, what charge should I put in here for the iron to make this expression equal 0? Well, it has to be a 2. So iron, in this case, we worked it backwards, has to be a +2 charge. +2 plus -2 gets me 0. So what we're really saying is the name we would have to give this compound is not just iron oxide, is iron Roman numeral 2 oxide. Okay? So this can be a little bit frustrating for people doing this the first time. It's very tempting just to write iron oxide and move on. You have to learn to recognize transition metals from other transition metals. And I said a few minutes ago that you actually have to use Roman numerals for transition metals 99% of the time, and there's a couple notable exceptions. And the one is for transition metals that only form one charge, and the most notable example for that is silver. Silver forms a +1 charge. It is a transition metal, but it does not have multiple charges. So in this case, if I wanted to name an ionic compound with silver in it, I technically would not have to use a Roman numeral. Now, I'm not going to mark you wrong if you use it, but if you use this on the online homework, it will mark you wrong if you write in a silver Roman numeral 1 chloride, for example. Okay? There is this handy little naming flowchart for ionic compounds, and I will let you guys go through this. I want to do one more example because the NH4 plus here reminded me of the example. NH4 is an interesting polyatomic ion. It looks like ammonia. You might be familiar to say that. But the NH4 ion, that is all of this as a +1 charge. It's one of the only +1 ions we have. So if I was going to write this in a compound, let's say I wanted to combine NH4 with the carbonate ion. We know that carbonate is a -2. I know that I have a +1 from here and a -2 from the carbonate, and I know this has to equal 0. Do I need more pluses or minuses? Well, to make this work, I would need 1 more plus 1. That just means I need 1 more ammonium. So I need to have another NH4 here to get my additional plus. So I have 2 plus 1 ammoniums. Well, this is an interesting case because you actually need parentheses initially because you need 2 ammoniums. So that's not a big deal. We just write our ammonium, and that is ammonium, not ammonia. Write our ammonia with parentheses with a subscript followed by our carbonate. I'll ask you, why don't I need a parentheses around the carbonate? And you would say, because I only need 1 of the carbonate species in this formula. So to name this, because I have a polyatomic ion in both places, I just say the name of the polyatomic ion in both times. Ammonium carbonate. Okay? There are a certain type of ionic compounds that actually have water, and these things are called hydrates. And I don't mean these compounds like have liquid water in them or ice or very cold. We actually have the water incorporate itself into the crystal structure of the material. So if you were looking at this material, if you were looking at a material like a hydrate on an atomic scale, in addition to the atoms that were in there, there will also be a water molecule attached to the structure. Again, not as a liquid, not as a gas, not as something frozen, just part of the crystal structure. So an example of a popular hydrate would be this blue substance here. It ends up looking like blue sand, and when we do this in class, I'll pass it out and allow you to touch it, and it looks like blue sand, but it actually has water in it. The magnesium sulfate heptahydrate is actually what we would normally call Epsom salts. And if you notice, the way we write this is use a little dot. The dot represents the hydrate, and it tells you the number of hydrates that go with every single molecule. So this molecule is barium chloride dihydrate. So every 1 molecule of barium chloride, I use the term molecule, technically incorrect here, but we'll kind of go with it right now. Every 1 molecule of barium chloride would have 2 water molecules attached. Every 1 molecule of magnesium sulfate would have 7 water molecules. Okay, so you see this type of thing once in a while. The interesting thing is you can drive away this water of hydration just by heating. So you can take our copper sulfate penta being 5, hydrate. You can take the water out of it just by heating it, and it actually changes color, and we will do that in a lab. As I mentioned last time in class, there's a very specific definition of a molecule as opposed to what I like to call a network structure. A network structure makes many, many, many compounds that repeat over and over again. Molecules are single isolated bits of matter that cannot connect with each other. A great example of that is water or carbon dioxide. A water molecule is simply 3 individual atoms that can never form another chemical bond with another molecule. They can form different types of bonds we call intermolecular forces, but not chemical bonds. There are diatomic molecules like hydrogen that have 2 of the same atom, and there are other diatomics, nitrogen, oxygen, fluorine, chlorine, and bromine. We don't name these dinitrogen or dioxygen, we just call them oxygen because that is how that element is found naturally. There are multiple ways we can describe formulas, and we might be splitting hairs a little bit here, but typically when we talk about a chemical formula, we're just writing a formula that describes the composition of the substance, and a molecular formula shows the exact number of atoms in each element of the molecule. We have different representations of molecules. This would be a chemical formula, and this is technically a Lewis structure. This might be another form of a Lewis structure. This is the ball and stick model. This is or often called a structural formula. The model here, HOH, is often called a structural formula. And this representation of water would be something we call a space-filling model. Understand that these basically all represent the same thing. I will generally use the term chemical formula over molecular formula just for simplicity. So as a sample problem, we have a ball and stick model of ethanol, and we want to write the molecular formula of this. We just need to basically count the atoms. Um, and it's understandable if you don't know what these atoms are. In general, the whites are hydrogen and blacks are carbon. Carbon can make many connections. If you notice here, each carbon atom ends up making 1, 2, 3, 4 connections. Hydrogens can make 1 connection. Oxygens have to make 2. So the right over here is an oxygen. Um, Typically, when we write compounds, we start with nonmetals first. Because this is kind of an organic compound, we'll start with a carbon, and then the hydrogen or the oxygen can kind of come before each other. And there's no great rule on this. You kind of just have to remember it. But to write the formula, we just count the number of atoms that are here. I have 2 carbons, and I have 1, 2, 3, 4, 5, 6 hydrogens, and 1 oxygen. If you do have only 1 of something, you do not need to write the 1 as a subscript. No subscript written after the oxygen it's understood to be 1. There is another class of compounds that we name, and they are what we call molecular compounds. And these are compounds that typically only have nonmetals in them. So you can identify a nonmetal or a molecular compound just by looking to see what types of atoms are present. And typically they are just nonmetals bonded to nonmetals. A great example would be something like carbon dioxide are both nonmetals. This is a molecular compound. H2O, sugar, C6, or glucose rather, C6H12O6. These are all nonmetals, and so therefore they are molecular, and as we'll learn later, they have covalent bonds versus ionic bonds. The naming system for molecular compounds is really straightforward. There's no Roman numerals. We typically just say the name of the first element. The last element, we need to use a prefix. So this is called carbon dioxide. The first element, we say the name. The last element, we have to use the "ide" version, and we have to use a prefix. The prefix for 2 is di, so this is carbon dioxide. We get to complex compounds like this. This is indeed complex. If you have more than 1 element for the first element, you need a prefix as well. This is a terrible example for this. A better example would be something like N2O4. So the first element is not alone. There's more than 1. So this would be dinitrogen, and then the 4 for oxygen will be tetraoxide. So this becomes dinitrogen tetroxide. Yes, we get rid of the A. Instead of writing tetraoxide, I suppose you could. We just write tetroxide. This is 1 element, no subscript, so this is carbon dioxide. It's a really straightforward naming system, and people seem to prefer it. There are some compounds that just kind of have their own names, and we don't usually give them other names, and those are not on this list. Oh, here they are. So these are compounds. We don't typically name water. Water as dinitrogen monoxide. H2S is hydrogen sulfide. H2O is water. pH3 is phosphane. NH3 is ammonia instead of nitrogen trihydride. I don't have a good reason for it, but there's some things that just don't have a true molecular name. So as a quick example, if you wanted to name these chemicals, the nitrogen and 3 fluorines, because there's only 1 nitrogen, we would just say nitrogen. And there's 3 fluorines, we would say trifluoride. This is nitrogen trifluoride. And I think we did this example before. This is 2 out front, dinitrogen, and then tetraoxide, or just tetroxide. Okay, in an effort to keep this lecture short, this is my very last slide. I know we're at 1 hour and 9 minutes right now. We also have acids, and acids are things that typically have a hydrogen listed out front, and that's a good way to spot an acid. There are a lot of them, and there are rules for naming acids, and I am not going to really test you on that. There are some acids you should just know because we use them very often in class. HCl here being the most common. This is hydrochloric acid. And there's a couple other that you should know, and we'll just kind of pick them up as time goes on. So anyways, this is lecture 2. This covers chapter 2 of the book, and I hope you enjoy this lecture. If you have any questions whatsoever, do not hesitate to contact me, please. And I hope you have a good week. Okay, see you then.